This is MSJ Chem. In this video, I'll be looking at the states of matter. The three states of matter we look at in this video are solid, liquid, and gas. Here we can see the particle arrangement for each of the states of matter. The particles in a solid are held in fixed positions. Therefore, solids have a fixed shape and a fixed volume. In a liquid, the particles are able to move more freely than in a solid. Therefore, liquids have a fixed volume but no fixed shape. And finally, we have a gas. In a gas, the particles move freely at high speeds with very weak forces of attraction between the particles. For these reasons, gases have neither a fixed volume nor a fixed shape. Next, we look at changes of state. So going from left to right, we have a solid to a liquid, which is melting. Liquid to gas can be either evaporation or boiling. The change of state from a solid directly to a gas with no liquid phase is known as sublimation. So next we'll go from right to left. A gas changing state to a liquid is condensation. A liquid to a solid is freezing. The change of state from a gas directly to a solid with no liquid phase is known as deposition. And finally, we look at state symbols. State symbols show the physical state of a substance. S stands for solid, L for liquid, G for gas, and AQ for aqueous. AQ is used for solutions formed by dissolving a solid in a liquid. So here we have an example of a chemical reaction that involves all four state symbols. So in the reaction, solid sodium reacts with water, which is a liquid, to form an aqueous solution of sodium hydroxide and hydrogen gas. This is MSJ Chem. In this video, I'll be looking at physical and chemical changes. Let's start by looking at physical changes. In a physical change, no new substances are produced. The melting of ice, which we can see in the picture on the left, is an example of a physical change. When ice melts, no new substances are produced. Instead, water in the solid state changes to water in the liquid state. Because there are no new substances being produced, this is an example of a physical change. Next, we look at two more examples of physical changes: evaporation and sublimation. On the left, we have the evaporation of bromine, in which bromine in the liquid state changes to bromine in the gaseous state. On the right, we have the sublimation of iodine, in which iodine in the solid state changes to iodine in the gaseous state. Because both these examples are physical changes, no new substances are being produced. Next, we look at chemical changes. A chemical change results in the formation of new chemical substances. In a chemical reaction, the atoms in the reactants are rearranged to form new products. Here we have an example of a combustion reaction in which methane reacts with oxygen to form carbon dioxide and water. The first thing we notice about this reaction is that there are the same number of atoms in the reactants as there are in the products. The law of conservation of mass states that in a chemical reaction, matter is not created or destroyed. The second thing we notice is that the atoms of the reactants have been rearranged to form new products. For example, the carbon atom that made up the methane molecule is now part of the carbon dioxide molecule, and the oxygen atoms that made up the oxygen molecules are now part of the carbon dioxide and water molecules. So from this example, we can see that in a chemical change, the atoms in the reactants are rearranged to form new chemical substances. This is MSJ Chem. In this video, I'll be looking at elements, compounds, and mixtures. Matter can be divided into pure substances or mixtures. Pure substances include elements and compounds. Mixtures can be either homogeneous or heterogeneous. We'll start by looking at elements. An element is a substance that cannot be broken down into a simpler substance by chemical means. All known elements can be found on the periodic table. In the periodic table, elements are arranged in order of increasing atomic number. starting with hydrogen. The structure of the periodic table is covered in a later video. Some elements exist as diatomic molecules. A molecule is an electrically neutral group of two or more atoms bonded together. Examples of diatomic molecules include hydrogen, chlorine, oxygen, and nitrogen. Next, we look at compounds. A compound is formed from two or more different elements chemically joined in a fixed ratio. Examples of compounds include water, ethanol, and sodium chloride. Both water and ethanol exist as molecules. Sodium chloride does not exist as molecules, instead it has a lattice structure. The different types of bonding and structure will be covered in topic 4. Compounds have different properties from the elements that they are made from. An example of this is the reaction of sodium with chlorine to produce sodium chloride. Sodium is a reactive metal and chlorine is a poisonous yellow-green gas. Together they react to form sodium chloride, which is also known as salt. The compound formed, which is sodium chloride, has very different properties from the elements from which it is made from. And finally, we look at mixtures. Mixtures contain more than one element and/or compound that are not chemically bonded together and so retain their individual properties. Mixtures can be homogeneous or heterogeneous. Homogeneous mixtures have a constant composition throughout. An example is salt water. Heterogeneous mixtures have visibly different substances or phases. An example is a mixture of oil and water. This is MSJ Chem. In this video, I'll be looking at balancing chemical equations. The law of the conservation of mass states that mass is conserved in a chemical reaction. This means that the total mass of the products must be equal to the total mass of the reactants. So here we have an example with the reaction of methane and oxygen to produce carbon dioxide and water. The first point to note is that we have the same number of atoms in the reactants as we do in the products. Next, if we add up the mass of the reactants and the products, we can see we get the same value for both. This shows us that mass is conserved in a chemical reaction. So to balance a chemical equation, we can only change the numbers in front of the reactants and products. These are called coefficients. So next we look at an example. In this unbalanced equation, we have the reaction of sodium with chlorine to produce sodium chloride. So the first step to balance this equation is to count the number of atoms in both the reactants and the products. So in the reactants, we have one sodium atom and two chlorine atoms. In the products, we have one sodium atom and one chlorine atom. To balance this equation, we put a 2 in front of the sodium and a 2 in front of the sodium chloride. So we now have the same number of atoms in the reactants and the products. In our next example, we have the unbalanced equation for the reaction of calcium carbonate with hydrochloric acid to form calcium chloride, water, and carbon dioxide. So once again, to balance the equation, we need to count the number of atoms in the reactants and the products. So in the reactants, we have one calcium atom, one carbon atom, one hydrogen atom, 3 oxygen atoms, and one chlorine atom. In the products, we have one calcium, one carbon, 2 hydrogens, 3 oxygens, and 2 chlorines. So by changing the coefficient in front of the HCl from a 1 to a 2, we now have the same number of atoms in the reactants and the products. In our next example, we have the unbalanced equation for the reaction of hexane, C6H14, with oxygen to produce carbon dioxide and water. So in the reactants, we have 6 carbon atoms, 14 hydrogen atoms, and 2 oxygen atoms. In the products, we have 1 carbon, 2 hydrogen, and 3 oxygen atoms. So to balance this equation, we need to put 2 in front of the hexane, 19 in front of the oxygen, 12 in front of the carbon dioxide, and 14 in front of the water. And we now have the same number of atoms in the reactants and the products. In our final example, we have the unbalanced equation for the reaction of zinc with silver nitrate to produce zinc nitrate and silver. So in the reactants we have 1 zinc, 1 silver, 1 nitrogen and 3 oxygen atoms. In the products we have 1 zinc, 1 silver, 2 nitrogen and 6 oxygen atoms. So to balance the equation we need to put a 2 in front of the silver nitrate and a 2 in front of the silver, which gives us the same number of atoms in the reactants and the products. This is MSJ Chem. In this video I'll be looking at atom economy. Here we have the equation for calculating percentage atom economy that appears in the IB data booklet. So that's percentage atom economy equals the molar mass of the desired product divided by the molar mass of all reactants multiplied by 100. There are other versions of the equation, and they are atom economy equals mass of desired product divided by mass of all reactants multiplied by 100, and mass of desired product divided by mass of all products multiplied by 100. To calculate the atom economy for a reaction, either one of these equations can be used. In this video, I'll be using the top equation because this one appears in the IB data booklet. Next we look at an example. Iron is produced by the reduction of iron oxide in a blast furnace. Calculate the atom economy of the reaction. Here we have the balanced chemical equation for the reaction. Iron oxide reacts with carbon monoxide to form iron and carbon dioxide. We'll start by finding the total of all the molar masses of the atoms in the reactants. So we have 2 atoms of iron, so that's 2 multiplied by the molar mass of iron, which is 55.85. We have 6 atoms of oxygen, so that's 6 multiplied by the molar mass of oxygen, which is 16.00. And we have 3 carbon atoms, so that's 3 multiplied by the molar mass of carbon, which is 12.01. When we add these together, we get a total of 243.7. Next, we find the total of the molar masses of all the atoms in the desired product, which in this case is iron. So that's 2 multiplied by the molar mass of iron, which is 55.85. And this gives us 111.7. Next, we'll use the equation to calculate the percentage atom economy. The total of the molar masses of our desired product, which was iron, is 111.7. The total of the molar masses of the reactants was 243.7. When we do this calculation, we get a percentage atom economy of 46%, which I've rounded to 2 significant figures. This percentage atom economy tells us that 54% by mass of the reactants do not end up in the desired product. In other words, they are wasted. The higher the atom economy for a chemical reaction, the less waste is produced and the more efficient the reaction is. This is MSJ Chem. In this video, I'll be looking at the mole concept. Let's start the video by looking at some questions. How many carbon atoms are there in 1 mole of ethanol? How many hydrogen atoms are there in 2 moles of methane? How many sodium ions are there in 1 mole of sodium chloride? And what is the total number of ions in 0.5 moles of ammonium carbonate? To answer these questions, we need to understand the mole concept. At the end of the video, we'll come back to these questions to see the answers. The mole is the SI unit for amount of substance. 1 mole contains exactly 6.02214.076 times 10 to the 23 elementary entities. This number, which is known as the Avogadro number, is usually rounded to 3 significant figures, which we can see here. The Avogadro constant, which is given the symbol L or Na, is numerically equivalent to the Avogadro number. The difference between the two is that the Avogadro number is dimensionless, in that it has no units. The unit of the Avogadro constant is the reciprocal of the amount of substance. So next, we'll have a look at some examples of elementary entities. In this table, we have examples of elementary entities. An elementary entity can be an atom, a molecule, an ion, or a formula unit. In the second column, we have the number of elementary entities in 1 mole. So 1 mole of atoms contains 6.02 times 10 to the 23 atoms. 1 mole of molecules contains 6.02 times 10 to the 23 molecules. 1 mole of ions contains 6.02 times 10 to the 23 ions. And 1 mole of formula units contains 6.02 times 10 to the 23 formula units. So from this table, we can see that 1 mole of substance always contains the same number of particles, which is 6.02 times 10 to the 23. So next, we'll look at some examples. In our first example, we'll determine the number of chlorine molecules and chlorine atoms in 1 mole of chlorine gas. Chlorine is a diatomic molecule with the formula Cl2. 1 molecule of chlorine gas consists of 2 chlorine atoms bonded together by a single covalent bond. So in 1 mole of chlorine gas, we have 6.02 times 10 to the 23 molecules of chlorine. In terms of chlorine atoms, we have 2 times the Avogadro constant. This is because 1 molecule of chlorine consists of 2 chlorine atoms. So in 1 mole of chlorine gas, we have 1.20 times 10 to the 24 chlorine atoms. In our next example, we'll determine the number of hydrogen atoms and oxygen atoms in 0.5 moles of water. 1 water molecule consists of 1 oxygen atom and 2 hydrogen atoms. And in 0.5 moles of water, we have 0.5 times 6.02 times 10 to the 23 number of water molecules. So for the number of hydrogen atoms, we multiply 2 times 0.5 times the Avogadro constant, which gives a total of 6.02 times 10 to the 23 hydrogen atoms. For the number of oxygen atoms, we multiply 0.5 by the Avogadro constant, which gives us 3.01 times 10 to the 23 oxygen atoms. In the next example, we'll determine the number of carbon atoms, hydrogen atoms, and oxygen atoms in 0.25 moles of ethanol. 1 molecule of ethanol consists of 2 carbon atoms, 1 oxygen atom, and 6 hydrogen atoms. In 0.25 moles of ethanol, we have 0.25 times 6.02 times 10 to the 23 number of ethanol molecules. So for the number of carbon atoms, we multiply 2 by 0.25 by the Avogadro constant, which gives us 3.01 times 10 to the 23 carbon atoms. For the number of hydrogen atoms, we multiply 6 by 0.25 by the Avogadro constant, which gives us 9.03 times 10 to the 23 hydrogen atoms. And for the number of oxygen atoms, we multiply 0.25 by the Avogadro constant, which gives us 1.51 times 10 to the 23 oxygen atoms. In the next example, we'll determine the number of magnesium ions and chloride ions in 1 mole of magnesium chloride. Magnesium chloride is an ionic compound, which is made up of magnesium ions and chloride ions. In 1 mole of magnesium chloride, we have 6.02 times 10 to the 23 formula units. The formula for magnesium chloride is MgCl2. This tells us the ratio of magnesium ions to chloride ions is 1 to 2. So for the number of magnesium ions, we have 6.02 times 10 to the 23. And for the number of chloride ions, we have 2 times the Avogadro constant, which gives us 1.20 times 10 to the 24 chloride ions. So we'll end the video by going back to the questions we looked at the start of the video. The first question was, how many carbon atoms are there in 1 mole of ethanol? And the answer is 1.20 times 10 to the 24 carbon atoms. In 1 molecule of ethanol, there are 2 carbon atoms. So to find the number of carbon atoms in 1 mole, we multiply 2 by the Avogadro constant. The next question was, how many hydrogen atoms are there in 2 moles of methane? And the answer is 4.82 times 10 to the 24 hydrogen atoms. 1 molecule of methane has 4 hydrogen atoms. So the calculation is 2 multiplied by 4 and then multiplied by the Avogadro constant. The third question is, how many sodium ions are there in 1 mole of sodium chloride? And the answer is 6.02 times 10 to the 23 sodium ions. In 1 formula unit of sodium chloride, the ratio of sodium to chloride ions is 1 to 1. So in 1 mole of sodium chloride, we have 1 mole of sodium ions and 1 mole of chloride ions. And the last question is, what is the total number of ions in 0.5 moles of ammonium carbonate? And the answer is 9.03 times 10 to the 23 ions. In 1 formula unit of ammonium carbonate, we have 1 carbonate ion and 2 ammonium ions. So we multiply 0.5 by 3 and then by the Avogadro constant. So that's all from this video. In the second part, I'll be looking at more examples involving the mole concept. This is MSJ Chem. In this video, I'll be looking at relative atomic mass and relative molecular mass. So we'll start with the definition of relative atomic mass. Relative atomic mass is the weighted average mass of the naturally occurring isotopes of an element relative to 1/12 the mass of an atom of carbon-12. The relative atomic mass scale is based on the isotope carbon-12, which has a mass of exactly 12 AMU. On the left, we can see the symbol for the isotope carbon-12. It is to this isotope that the masses of other atoms are compared. The relative atomic masses of elements can be found on a periodic table. Hydrogen has a relative atomic mass of 1.01. Magnesium has a relative atomic mass of 24.31. Chlorine has a relative atomic mass of 35.45. And iron has a relative atomic mass of 55.85. As you can see, relative atomic masses are not usually whole numbers. This is because they are a weighted average of the naturally occurring isotopes of that element. We'll look at how to calculate relative atomic mass later in the video. Note that because this is a relative scale, relative atomic masses are dimensionless, in that they have no units. Next, we'll look at how the masses of atoms can be compared using their relative atomic masses. In this table we have the element, its relative atomic mass, and its mass compared to the isotope carbon-12. The first example is hydrogen, which has a relative atomic mass of 1.01. This means that an atom of hydrogen is approximately 12 times lighter than an atom of carbon-12. Next is helium, which has a relative atomic mass of 4.00, which means that a helium atom is approximately 3 times lighter than an atom of carbon-12. Next is magnesium, with a relative atomic mass of 24.31, which means that a magnesium atom is approximately 2 times heavier than an atom of carbon-12. Next is phosphorus, with a relative atomic mass of 30.07, and is approximately 2.5 times heavier than an atom of carbon-12. And finally, we have chlorine, with a relative atomic mass of 35.45, which is approximately 3 times heavier than an atom of carbon-12. We can also use relative atomic masses to compare the masses of different atoms. For example, an atom of helium is approximately 4 times heavier than an atom of hydrogen, and an atom of magnesium is approximately 6 times heavier than an atom of helium. So from this table, we can see that relative atomic mass values can be used to compare the masses of different atoms to carbon-12, as well as each other. Next, we look at how to calculate the relative atomic mass of an element. In this table, we have the 3 naturally occurring isotopes of magnesium. They are magnesium-24, magnesium-25, and magnesium-26. In the second column, we have their relative abundances. So we'll use these values to calculate the relative atomic mass of magnesium. To do this, we multiply the mass of each isotope by its relative abundance. We then add these together and divide by 100 to get the mass of one atom. So using these values, we get a relative atomic mass for magnesium of 24.32. Note that because it's a relative scale, there are no units. In this slide, we'll look at relative molecular mass. Relative molecular mass is the weighted average mass of a molecule relative to 1/12 the mass of an atom of carbon-12. The relative molecular mass of a molecule is the sum of the relative atomic masses of the atoms in the molecule. So in this table we have some examples. Starting with hydrogen, which is a diatomic molecule consisting of two hydrogen atoms bonded together. Each hydrogen atom has a relative atomic mass of 1.01. So we multiply this value by 2 to get a relative molecular mass of 2.02. The next example is H2O, which is composed of two hydrogen atoms and one oxygen atom. If we add up the relative atomic masses of the atoms, we get a relative molecular mass of 18.02. And finally, we have C2H6, which is ethane. A molecule of ethane is composed of two carbon atoms and 6 hydrogen atoms. If we add up the relative atomic masses of the atoms, we get a relative molecular mass of 30.08. Note that like relative atomic masses, relative molecular masses do not have units. We'll end the video by looking at relative formula mass. The term relative formula mass is mostly used for compounds that do not form molecules, such as ionic compounds. On the left, we can see the structure of an ionic compound. Because ionic compounds do not form molecules, we use the term relative formula mass instead of relative molecular mass. For example, the relative formula mass of sodium chloride, which is NaCl, is 58.44. We calculate this by adding together the relative atomic masses of sodium and chlorine. So that's all from this video. In the next video, I'll be looking at molar mass. This is MSJ Chem. In this video, I'll be looking at molar mass. So let's start with a definition. Molar mass is the mass in grams of 1 mole of a substance. The unit for molar mass is grams per mole. As we saw in a previous video, 1 mole of substance contains 6.02 times 10 to the 23 particles. The molar mass of a substance is numerically equal to its relative atomic mass. The relative atomic masses of elements can be found on the periodic table. Here we can see the relative atomic masses of carbon, magnesium, sulfur, and iron. As mentioned previously, the molar mass is numerically equal to the relative atomic mass. However, they are not the same. One difference is that relative atomic mass is dimensionless, in that it has no units, whereas molar mass has units of grams per mole. So in the next slide, we look at how to convert from relative atomic mass to molar mass. So to convert from relative atomic mass to molar mass, multiply by the molar mass constant, which is approximately equal to 1 gram per mole. In this table, we have the elements we saw in the previous slide, their relative atomic masses and their molar masses. Starting with carbon, which has a relative atomic mass of 12.01. The molar mass of carbon is 12.01 grams per mole. Next is magnesium, which has a relative atomic mass of 24.31. Its molar mass is 24.31 grams per mole. Next is sulfur, which has a relative atomic mass of 32.07. And its molar mass is 32.07 grams per mole. And finally we have iron, which has a relative atomic mass of 55.85 and a molar mass of 55.85 grams per mole. So from this table we can see that relative atomic mass and molar mass are numerically equal. However, molar mass has units of grams per mole, whereas relative atomic mass has no units. Next, we'll look at how to calculate the molar mass of a compound. In this example, we'll determine the molar mass of ethanol, which has the molecular formula C2H5OH, On the right, we can see one molecule of ethanol. One molecule of ethanol is made up of 2 carbon atoms, 1 oxygen atom, and 6 hydrogen atoms. On the left, we can see the relative atomic masses of carbon, oxygen, and hydrogen. First, we'll calculate the relative molecular mass of ethanol, which is 2 times 12.01 plus 16 plus 6 times 1.01, which gives us a relative molecular mass of 46.08. Because this is the relative molecular mass, it has no units. To convert to molar mass, we multiply the relative molecular mass by the molar mass constant, and this gives a molar mass of 46.08 grams per mole. So to summarize, the molar mass of ethanol is 46.08 grams per mole. This tells us that 1 mole of ethanol has a mass of 46.08 grams. So next we'll look at some more examples. In this table we have the substance, the relative molecular mass or relative formula mass, and the molar mass. Starting with molecular oxygen, which has the formula O2. The relative molecular mass of oxygen is 32.00. Its molar mass is 32.00 grams per mole. Next, we have water, which has the formula H2O. Its relative molecular mass is 18.02, and its molar mass is 18.02 grams per mole. Next is methane, which has the formula CH4. Its relative molecular mass is 16.05, and its molar mass is 16.05 grams per mole. Next, we have sodium chloride. The relative formula mass of sodium chloride is 58.44. The molar mass of sodium chloride is 58.44 grams per mole. Next is ammonium carbonate. Its relative formula mass is 96.11, and its molar mass is 96.11 grams per mole. And finally, we have aluminium oxide. Its relative formula mass is 101.96, and its molar mass is 101.96 grams per mole. So this highlights the point that relative molecular mass or relative formula mass and molar mass are numerically equal. The difference being that relative molecular mass and relative formula mass do not have units, whereas molar mass has the units of grams per mole. This is MSJ Chem. In this video, I'll be looking at how to calculate the amount of substance. So we'll start the video by looking at how to calculate the amount in moles of a substance from its mass and molar mass. So in this equation, we have amount of substance in moles is equal to the mass of the substance divided by its molar mass. The unit for mass is usually grams, and molar mass grams per mole. This equation can also be written as N, which is amount in moles, equals lowercase m, which is mass in grams, divided by uppercase M, which is molar mass. On the right, we have an easier way to remember this equation, where N is amount in moles, lowercase m is mass in grams, and the uppercase M is molar mass. The equation that we looked at in the previous slide can be rearranged to calculate either mass in grams or molar mass. To calculate the mass in grams, multiply the amount in moles by the molar mass. And to calculate the molar mass, divide the mass in grams by the amount in moles. We'll look at the use of these equations in a separate video. So next, we look at some examples. The first example is to calculate the amount in moles of oxygen in a 16-gram sample. The first step is to determine the molar mass of the substance. Oxygen is a diatomic molecule, therefore we need to multiply the relative atomic mass of oxygen by 2, which gives us a molar mass of 32 grams per mole. In the next step, we divide the mass of oxygen by its molar mass. So that's 16 grams divided by the molar mass, which is 32 grams per mole. And this gives us the amount of oxygen, which is 0.5 moles. In the next example, we'll calculate the amount in moles of H2O in a 100-gram sample. So just like in the previous example, the first step is to determine the molar mass of H2O. The relative atomic mass of oxygen is 16, and for hydrogen it's 1.01. So for the molar mass we have 16 plus 2 times 1.01, which gives us 18.02 grams per mole. Next, we divide the mass in grams by the molar mass, which gives us an amount of H2O of 5.549 moles. In the last example using this equation, we have calculate the amount in moles of sodium chloride in a 50-gram sample. To determine the molar mass of sodium chloride, we add the relative atomic mass of sodium and chlorine, which gives us 58.44 grams per mole. Next, we divide the mass by the molar mass, and this gives us an amount of sodium chloride of 0.8556 moles. Next, we look at how to calculate the amount in moles of a substance from its volume and concentration. So the equation is amount in moles equals concentration in moles per decimeter cubed multiplied by the volume in decimeters cubed. This can also be written as N, which is amount in moles, equals C, which is concentration in moles per decimeter cubed, multiplied by V, which is the volume in decimeters cubed. Here we have an easy way to remember this equation. N equals CV. Note that the volume in this equation must be in decimeters cubed. To convert between centimeters cubed and decimeters cubed, multiply the volume in centimeters cubed by 1 over 1,000. For example, 1 centimeter cubed is equal to 0.001 decimeters cubed. The equation that we looked at in the previous slide can be rearranged to calculate concentration or volume. To calculate the concentration in moles per decimeter cubed, divide the amount in moles by the volume in decimeters cubed. And to calculate the volume in decimeters cubed, divide the amount in moles by the concentration in moles per decimeter cubed. The use of these equations will be covered in a separate video. In our first example, we'll calculate the amount in moles of hydrochloric acid in 100 centimeters cubed of a 0.5 mole per decimeter cubed solution. So the first step is to convert the volume in centimeters cubed to decimeters cubed. So 100 centimeters cubed is equal to 0.1 decimeters cubed. The next step is to multiply the concentration in moles per decimeter cubed by the volume in decimeters cubed, and this gives us an amount of 0.05 moles. In the next example, we'll calculate the amount in moles of sodium hydroxide in 50 centimeters cubed of a 2 mole per decimeter cubed solution. So we'll start by converting the volume from centimeters cubed to decimeters cubed. We then multiply the concentration in moles per decimeter cubed by the volume in decimeters cubed, and this gives us an amount of 0.1 moles of sodium hydroxide. In our final example, we'll calculate the amount in moles of sodium chloride in 60 centimeters cubed of a 0.850 mole per decimeter cubed aqueous solution. So the first step is to convert the volume in centimeters cubed to decimeters cubed. We then multiply the concentration in moles per decimeter cubed by the volume in decimeters cubed, which gives us an amount of sodium chloride of 0.0510 moles. This is MSJ Chem. In this video, I'll be looking at how to calculate mass in grams from amount in moles. In a previous video, we looked at how to use this equation to calculate the amount in moles from mass in grams and molar mass. This equation can be rearranged to calculate mass in grams. So mass in grams equals amount in moles multiplied by molar mass. Here we have an easy way to remember this equation. Lowercase m, which is mass in grams, equals n, which is amount in moles, multiplied by uppercase M, which is molar mass. So next, we look at some examples. In our first example, we'll calculate the mass in grams of 0.6437 moles of calcium carbonate. The first step is to determine the molar mass of calcium carbonate. Here we have the relative atomic masses of calcium, carbon, and oxygen. When we add these together, we get a molar mass of 100.09 grams per mole. Next, we'll use the equation mass in grams equals amount in moles multiplied by the molar mass. So the amount in moles is 0.6437, and the molar mass is 100.09 grams per mole. And this gives us a mass of 64.43 grams. In the next example, we'll calculate the mass in grams of 0.8539 moles of aluminium chloride. So we'll start by determining the molar mass. The relative atomic mass of aluminium is 26.98, and for chlorine it's 35.45. When we add these together, we get a molar mass of 133.33 grams per mole. Next, we multiply the amount in moles by the molar mass, and this gives us a mass of 113.9 grams. In the final example, we'll calculate the mass in grams of 1.379 moles of glucose, which is C6H12O6. To determine the molar mass, we have the relative atomic mass of carbon, hydrogen, and oxygen, which gives us a molar mass of 180.18 grams per mole. We then multiply the amount in moles by the molar mass, which gives us a mass of 248.5 grams. In this video, we'll look at molar ratios. So the coefficients in a balanced equation tell us the mole ratios of reactants and products. Here's a fictional chemical reaction. We have 2A plus 3B makes C and 2D. So what this means is 2 moles of A, that's what the 2 in front means, react with 3 moles of B to form 1 mole of C and 2 moles of D. So these numbers in front, these are the coefficients, and they tell us the mole ratios of the reactants on the left side and the products on the right side. However, in the majority of chemical reactions, we usually have a reactant that is limiting and a reactant in excess. I have a separate video that covers limiting reactants, so in this video I'll focus on molar ratios. So here we have a real chemical reaction. We have calcium carbonate reacting with hydrochloric acid to form calcium chloride, water, and carbon dioxide. Now this equation is balanced. According to the balanced equation, 1 mole of calcium carbonate, if there's no number there, you assume it's a 1. That reacts with 2 moles of hydrochloric acid, and that forms 1 mole of calcium chloride, 1 mole of water, and 1 mole of carbon dioxide. So let's try an example. Assuming that HCl is in excess, so we have plenty of HCl, that makes calcium carbonate the limiting reactant. So what amount in moles of H2O can be produced from 0.667 moles of calcium carbonate? So we need to look at the ratio of calcium carbonate to water. So the ratio is 1 mole of calcium carbonate to 1 mole of water. So it's a 1-to-1 ratio. So therefore, if we have 0.667 moles of calcium carbonate, we will produce 0.667 moles of water because of this 1-to-1 ratio. Let's try another example. This time, assuming that calcium carbonate is in excess, which means that HCl is the limiting reactant, what amount in moles of CO2 can be produced from 1.15 moles of HCl? So we need to look at the ratio again. So the ratio of HCl to CO2 is 2-to-1. So we have 2 moles of HCl to 1 mole of CO2. So therefore, if we have 1.15 moles of HCl, we will produce half as much CO2 because of this 2-to-1 ratio. So therefore, we divide 1.15 by 2 to give us 0.575 moles of CO2. Let's have a look at one more example. Here we have aluminium reacting with hydrogen bromide to form aluminium bromide and hydrogen gas. So our first example, assuming that hydrogen bromide is in excess, which means that aluminium is the limiting reactant, what amount in moles of H2 can be produced from 3.64 moles of aluminium? So we look at the ratio, and the ratio of aluminium to hydrogen gas is a 2-to-3 ratio. Now if it makes it easier, you can simplify this ratio to 1 to 1.5. So therefore 3.64 moles of aluminium will produce, now because it's a 2-to-3 or a 1 to 1.5, you can just multiply this number of moles by 1.5. So therefore it's 3/2 or 1.5 times 3.64 equals 5.46 moles of hydrogen gas. And our final question, according to the same conditions, that means the hydrogen bromide is in excess, what amount in moles of aluminium bromide can be produced? So we look at the ratio of aluminium to aluminium bromide, and we can see it's a 2-to-2 ratio, and you can simplify that to 1-to-1. So therefore 3.64 moles of aluminium will produce the same amount, that's 3.64 moles of aluminium bromide. This is MSJ Chem. In this video I'll be looking at mole fraction and mole percent. Mole fraction is the amount in moles of one component in a mixture divided by the total amount in moles of all components in the mixture. Here we have the equation for mole fraction. From the equation, we can see that the mole fraction of a component of a mixture is equal to the amount in moles of that component divided by the total amount in moles of all components in the mixture. The mole percent is the mole fraction multiplied by 100. So next, we look at an example. A mixture of gases at STP consists of 250 cubic centimeters of nitrogen and 50 cubic centimeters of hydrogen. Determine the mole fraction and mole percent of each gas in the mixture. The first step is to calculate the amount in moles of nitrogen. To do this, we divide the volume of nitrogen in cubic decimeters by the molar volume of a gas, also in cubic decimeters. And this gives us 0.0110 moles. Next, we find the total amount in moles in the mixture. The total volume is 0.3 cubic decimeters, which we divide by the molar volume of a gas, also in cubic decimeters. And this gives us 0.0132 moles. So the mole fraction of nitrogen is the amount in moles of nitrogen divided by the total amount in moles of the mixture, which gives us a mole fraction of 0.833. To calculate the mole percent, we multiply the mole fraction by 100, which gives us 83.3%. So next we'll calculate the mole fraction of hydrogen. The first step is to calculate the amount in moles of hydrogen. To do this, we divide the volume in cubic decimeters by the molar volume of a gas in cubic decimeters, which gives us 2.20 times 10 to the negative 3 moles. So to calculate the mole fraction, we divide the amount in moles of hydrogen by the total amount in moles of the mixture, which gives us a mole fraction of 0.167 and a mole percent of 16.7%. Next we look at a quicker way of solving the problem. Because the mixture of gases is at a constant temperature and pressure, we can treat the molar ratios as volume ratios. To calculate the mole fraction of nitrogen, we divide the volume of nitrogen by the total volume of the mixture, which gives us the same answer as before, which is 0.833, and a mole percent of 83.3%. To calculate the mole fraction of hydrogen, we divide the volume of hydrogen by the total volume of the mixture, which gives us the same answer as before, which is 0.167, and a mole percent of 16.7%. Note that the sum of the mole fractions must be equal to 1, and the sum of the mole percents must be equal to 100%. Next, we look at one more example, this time involving an aqueous solution. 10 grams of sodium chloride is dissolved in 50 grams of water. Determine the mole fraction and mole percent of each component of the solution. So the first step is to calculate the amount in moles of sodium chloride. To do this, we divide the mass by the molar mass, which gives us 0.171 moles. Next, we'll calculate the amount in moles of water. So when we divide the mass of water by its molar mass, we get 2.77 moles. We can then calculate the total number of moles in the solution. So that's 2.77 plus 0.171, which equals 2.94 moles. To calculate the mole fraction of sodium chloride, we divide the amount in moles of sodium chloride by the total amount in moles of the solution, which gives us a mole fraction of 0.058 and a mole percent of 5.8%. To calculate the mole fraction of the water, we divide the amount in moles of water by the total amount in moles of the solution, which gives us a mole fraction of 0.942 and a mole percent of 94.2%.
This is MSJ Chem. In this video, I'll be looking at calculating percentage composition by mass. So we'll start by looking at an example. Calculate the percentage composition by mass of sodium, sulfur and oxygen in sodium sulfate. To calculate the percentage composition by mass of an element, we divide the total mass of the element by the total mass of the compound and multiply by 100. The first step is to determine the molar mass of the compound. So we multiply the relative atomic mass of sodium by 2, we add the relative atomic mass of sulfur, and we add 4 times the relative atomic mass of oxygen, which gives us 142.05 grams per mole. Next, we'll calculate the percentage composition of sodium by mass. Because we have 2 sodium atoms in the compound, we multiply the relative atomic mass of sodium by 2, and then we divide by the molar mass of the compound. We then multiply by 100 to give us 32.37%. Next, we'll calculate the percentage composition of sulfur by mass. So we divide the mass of the sulfur by the mass of the compound and multiply by 100, which gives us 22.58%. And finally, we'll calculate the percentage composition of oxygen by mass. Because there are 4 oxygen atoms in the compound, we multiply the relative atomic mass of oxygen by 4. We then divide by the molar mass of the compound and multiply by 100, which gives us 45.05%. This is MSJ Chem. In this video, I'll be looking at empirical and molecular formulas. Let's start the video with a couple of definitions. The molecular formula is the actual number of atoms in a compound, and the empirical formula is the lowest whole number ratio of atoms in a compound. Here we can see the structure of butane, which is an organic compound. One molecule of butane has 4 carbon atoms and 10 hydrogen atoms. So the molecular formula of butane is C4H10. This is because there are 4 carbon atoms and 10 hydrogen atoms in one molecule of butane. The empirical formula of butane is C2H5. This is the lowest whole number ratio of atoms in the compound. As we can see, for butane, the molecular formula and the empirical formula are different. In some compounds, they can be the same. So next, we look at some more examples. In this table, we have the compound, its molecular formula, and its empirical formula. Starting with ethane, which has the molecular formula C2H6, and the empirical formula CH3. Next is propene, which has the molecular formula C3H6, and the empirical formula CH2. Glucose has the molecular formula C6H12O6, and its empirical formula is CH2O. Next, we have phosphorus pentoxide. Its molecular formula is P4O10 and its empirical formula is P2O5. Hydrogen peroxide has the molecular formula H2O2 and the empirical formula is HO. And finally, we have ethanol. The molecular formula for ethanol is C2H6O. And as we can see, the empirical formula is the same. So from this table, we can see that for some compounds, the molecular formula and empirical formula are different, but for some compounds, it's the same. The molecular formula of a compound can be determined from its empirical formula and its relative molecular mass. So let's look at an example. A compound has the empirical formula CH2O and a relative molecular mass of 180.18. Determine its molecular formula. The first step is to find the mass of the empirical formula. So here we have the relative atomic masses of the atoms in the empirical formula. They are carbon, hydrogen, and oxygen. If we add these together, we get a mass of 30.03. The next step is to divide the relative molecular mass by the mass of the empirical formula. So that's 180.18 divided by 30.03. And this gives us a value of 6. The final step is to multiply the empirical formula by 6. And this gives the molecular formula, which is C6H12O6. So that's all from this video. In the next video, I'll be looking at how to determine the empirical formula from percent composition. This is MSJ Chem. In this video, I'll be looking at how to calculate empirical formula from percent composition. Let's look at an example. An organic compound contains 62% carbon, 13.9% hydrogen, and 24.1% nitrogen by mass. Determine its empirical formula. The first step is to assume that we have 100 grams of the compound. So these percentages can be taken as masses in grams. So in 100 grams of the compound, we have 62 grams of carbon, 13.9 grams of hydrogen, and 24.1 grams of nitrogen. The second step is to convert from mass in grams to amount in moles. To do this, we'll divide the mass in grams by the molar mass. So for carbon, it's 62 grams divided by 12.01. For hydrogen, it's 13.9 grams divided by 1.01. And for nitrogen, it's 24.1 grams divided by 14.01. This gives us 5.16 moles of carbon, 13.8 moles of hydrogen, and 1.72 moles of nitrogen. The next step is to divide each amount in moles by the smallest value. So for carbon, we divide 5.16 by 1.72. For hydrogen, it's 13.8 divided by 1.72. And for nitrogen, it's 1.72 divided by 1.72. This gives us 3 for carbon, 8 for hydrogen, and 1 for nitrogen. And finally, we write the empirical formula, which is C3H8N. Next, we'll determine the molecular formula of the compound. So here we're told that the molar mass of the compound is 116.24 grams per mole. The first step is to determine the mass of the empirical formula. So the empirical formula had 3 carbon atoms, 8 hydrogen atoms, and 1 nitrogen atom. If we add these up, we get a mass of 58.12. Next, we divide the molar mass by the mass of the empirical formula. So that's 116.24 divided by 58.12, which gives us 2. The final step is to multiply the empirical formula by 2. So that's 2 times 3 for the carbon, 2 times 8 for the hydrogen, and 2 times 1 for the nitrogen. And this gives us the molecular formula, which is C6H16N2. Let's look at one more example. An organic compound contains 49.2% carbon, 6.95% hydrogen, and 43.85% oxygen by mass. Determine its empirical formula. So just like in the previous example, we'll treat these percentages as masses. So we have 49.20 grams of carbon, 6.95 grams of hydrogen, and 43.85 grams of oxygen. We then convert to amount in moles by dividing by the molar mass, which gives us 4.10 moles of carbon, 6.88 moles of hydrogen, and 2.74 moles of oxygen. The next step is to divide each amount in moles by the smallest value, which is 2.74. And this gives us 1.50 for carbon, 2.51 for hydrogen, and 1 for oxygen. Empirical formulas can only contain whole numbers. So we need to multiply each of these numbers by 2 to get 3 for carbon, 5 for hydrogen, and 2 for oxygen. And here we have the empirical formula, which is C3H5O2. This is MSJ Chem. In this video, I'll be looking at calculating empirical formula from experimental data. We start the experiment by measuring 10 centimeters of magnesium ribbon. Next, the magnesium ribbon is wrapped around a pencil to form a coil. To calculate the empirical formula, we must record the mass of the crucible and the lid, and the mass of the magnesium, the crucible, and the lid. As you can see, the mass of the crucible and the lid is 47.19 grams, and the mass of the magnesium, the crucible, and the lid is 47.30 grams. Next, the crucible is heated with a Bunsen burner. Here we can see the reaction starts to take place, with the magnesium glowing as it reacts with oxygen. The lid is opened now and again to let in oxygen for the reaction. Care must be taken not to lose too much white powder. Once all the magnesium has reacted, we are left with a white powder, which is magnesium oxide. When the crucible has cooled, the mass of the contents, crucible, and lid is recorded. As you can see, the mass has increased as the magnesium has reacted with the oxygen in the air. And here we have the results of the experiment. We have the mass of crucible and lid, the mass of magnesium crucible and lid, and the mass of the contents crucible and lid after heating. The next step is to determine the mass of magnesium. To do this, we subtract the mass of the crucible and the lid from the mass of the magnesium crucible and lid, which gives us 0.11 grams. To calculate the mass of oxygen, we subtract the mass of the magnesium crucible and lid from the mass of the contents crucible and lid, which gives us 0.07 grams. The next step is to calculate the amount in moles of magnesium and oxygen. To do this, we divide the mass of magnesium by the molar mass of magnesium, which gives us 4.52 times 10 to the negative 3 moles. For oxygen, we divide the mass of oxygen by the molar mass of oxygen, which is 16.00 grams per mole, and this gives us 4.38 times 10 to the negative 3 moles. The final step is to divide the amount in moles of magnesium and oxygen by the smallest amount. So when we divide by the lowest amount, which is 4.38 times 10 to the negative 3, we get the lowest whole number ratio of atoms in the compound. So from this experimental data, the empirical formula of magnesium oxide is MgO. In this experiment, it is quite common not to get a 1-to-1 ratio of magnesium to oxygen. Possible errors include the magnesium was not pure, the product was not only magnesium oxide, and the product was lost when the lid was removed. This is MSJ Chem. In this video, I'll be looking at calculating empirical formula from combustion analysis. So in this video, we'll calculate the empirical formula of menthol using combustion analysis. So menthol is an organic compound composed of carbon, hydrogen, and oxygen atoms. The complete combustion of 0.1005 grams of menthol produces 0.2829 grams of carbon dioxide and 0.1159 grams of water. So here we have the unbalanced equation for the complete combustion of menthol. In complete combustion, menthol reacts with an excess of oxygen to produce carbon dioxide and water. According to the data given, the complete combustion of 0.1005 grams of menthol produces 0.2829 grams of carbon dioxide and 0.1159 grams of water. So next, we'll use this data to calculate the empirical formula of menthol. So the first step is to calculate the mass of carbon in 0.2829 grams of carbon dioxide. To do this, we divide the mass of carbon in the molecule by the total mass of the carbon dioxide molecule, and then we multiply by the mass of carbon dioxide produced in the reaction. So that's 12.01 divided by 44.01 multiplied by 0.2829, which gives us 0.07720 grams of carbon. Next, we convert to amount in moles using the equation N, which is amount in moles, equals mass over molar mass, which gives us 6.428 times 10 to the negative 3 moles of carbon. Next, we'll calculate the mass of hydrogen in 0.1159 grams of H2O. We do this by dividing the mass of hydrogen in the molecule by the total mass of the water molecule, and then we multiply by the mass of water produced in the reaction. So there are 2 hydrogen atoms in 1 molecule of water, so that's 2.02 divided by 18.02. We then multiply that by the mass of water produced in the combustion reaction, which gives us 0.01299 grams of hydrogen. Next, we'll convert to amount in moles using the equation N equals mass over molar mass, which gives us 0.01286 moles of hydrogen. The next step is to calculate the mass of oxygen in 0.1005 grams of menthol. To do this, we subtract the mass of carbon and the mass of hydrogen from the original mass of menthol, which gives us 0.01031 grams of oxygen. So next we convert to amount in moles using the equation mass over molar mass, which gives us 6.444 times 10 to the negative 4 moles of oxygen. Now that we've calculated the amount in moles of carbon, hydrogen and oxygen, we need to divide each amount by the smallest to get the lowest whole number ratio. The smallest amount in moles was 6.444 times 10 to the negative 4. So we need to divide each amount in moles by this value. This gives us 10 for the carbon, 20 for the hydrogen, and 1 for the oxygen. So the empirical formula of menthol is C10H20O, which is the lowest whole number ratio of atoms in the compound. This is MSJ Chem. In this video, I'll be looking at the water of crystallization. The water of crystallization is the fixed number of water molecules present in one formula unit of a salt. In this picture on the left we have the hydrated salt copper 2 sulfate pentahydrate. On the right we have the anhydrous salt copper 2 sulfate. The difference between the two salts is the salt on the left still has the 5 water molecules attached to the salt. These 5 water molecules are the water of crystallization. The hydrated salt is named according to how many water molecules there are in the salt. So in this case the salt is named copper 2 sulfate pentahydrate because there are 5 water molecules. Upon heating, the blue copper sulfate pentahydrate decomposes, forming the white anhydrous salt and water vapor. On the left we can see the blue hydrated salt being heated, forming the white anhydrous salt. And here we have the equation for the decomposition of copper sulfate pentahydrate into the anhydrous salt and water vapor. Care must be taken as overheating of the anhydrous salt can cause further decomposition to take place. Next, we'll look at the experimental procedure for determining the water of crystallization. The first step is to measure the mass of an empty crucible and lid. Step 2 is add a known mass of the sample and record the mass. Step 3 is heat the crucible for 5 minutes, holding the lid at an angle so the gas can escape. Step 4 is after cooling, reweigh the crucible, lid and contents. And step 5 is repeat steps 3 and 4 until the mass remains constant. This is known as heating to constant mass. So next we'll determine the water of crystallization for the hydrated salt BaCl2xH2O from the following data. So in this table we have the mass of crucible and lid, the mass of crucible, lid and sample, the mass of crucible, lid and sample after first heating, and the mass of the crucible, lid and sample after second heating. Note that the mass of the crucible, lid and sample after first heating and second heating are the same. This is what is meant by heating to constant mass. So first we'll determine the mass of the hydrated sample. To do this, we subtract the mass of the crucible and lid from the mass of the crucible, lid and sample, which gives us 5.00 grams. Next, we determine the mass of water driven off when the sample was heated. To do this, we subtract the mass of crucible, lid and sample after heating from the mass of the crucible, lid and sample, which gives us 0.74 grams. And finally, we can determine the mass of the anhydrous BaCl2. To do this, we subtract the mass of water driven off when the sample was heated from the mass of the hydrated sample, which gives us 4.76 grams. Next, we need to convert from mass in grams to amount in moles. So we divide the mass of the anhydrous sample by its molar mass, which gives us 0.02 moles. Next, for the water, we divide the mass of water driven off by the molar mass of water, which gives us 0.04 moles. We then divide each of these values by the smallest to give us the lowest whole number ratio. So that's 1 for the anhydrous BaCl2 and 2 for the H2O. This gives us the formula for the hydrated salt, which is BaCl2 2H2O. The name of the salt is barium chloride dihydrate. Finally, we look at the assumptions made in the experiment.
The first assumption is that all mass lost is due to the loss of water. The second is that all water of crystallization is driven off. The third is that the crucible does not absorb water. And the last assumption is that the anhydrous barium chloride does not decompose further. This is MSJ Chem. In this video, I'll be looking at limiting and excess reactants. So let's start with a question. How many sandwiches can be made with 12 pieces of bread and 7 slices of ham? The answer is 6 sandwiches, which would require 12 pieces of bread and 6 slices of ham. In this example, the bread is limiting the number of sandwiches that can be made. And 1 slice of ham remains. So if this were a chemical reaction, the bread would be the limiting reactant and the ham would be the excess reactant. This is because the bread is limiting the number of sandwiches that we can make. And after all the bread has been used up, we have 1 slice of ham remaining. So next we look at how to determine the limiting reactant and excess reactant in a chemical reaction. So first we look at the definitions. The limiting reactant, also known as the limiting reagent, is the reactant that limits the amount of product that can be made. And the excess reactant is the reactant that remains when the limiting reactant is consumed. Next, we look at 3 steps to calculating the limiting reactant. The first step is to calculate the amount in moles of each reactant. The second step is to divide the amount of each reactant by its coefficient in the balanced equation. And after dividing, the lowest value is the limiting reactant. In our first example, 50 grams of N2H4 is reacted with 75 grams of N2O4. Determine the limiting and excess reactants. The first step is to determine the amount in moles of N2H4 and N2O4. Starting with N2H4, we divide the mass in grams by the molar mass, which gives us 1.56 moles. Next, we do the same thing for the N2O4. That's divide the mass in grams by the molar mass, which gives us 0.815 moles. Once we've determined the amount in moles of each reactant, we now need to divide by the coefficient. For N2H4, it's 1.56 divided by 2. The reason we divide by 2 is that the coefficient of the N2H4 in the balanced equation is 2, which gives us 0.780. And for N2O4, it's 0.815 divided by 1. Once again, we divide by 1 because the coefficient of the N2O4 is 1, which gives us 0.815. Next, we compare these two values to see which one is the lowest. So we can see that the value for the N2H4 is the lowest, therefore it is the limiting reactant. And N2O4 is the excess reactant. The next step in this example is to determine the amount of excess reactant that remains at the end of the reaction. To do this, we need to look at the molar ratio of N2H4 to N2O4. So from the balanced equation, we can see the ratio is 2 to 1. Next, we'll use the molar ratio to determine the amount in moles of N2O4 left at the end of the reaction. We have 1.56 moles of our limiting reactant, which is N2H4. We are then going to multiply by 1 over 2 because of the molar ratio we looked at earlier, and this gives us 0.780 moles of N2O4. So this is the amount in moles of N2O4 that react completely with 1.56 moles of our limiting reactant, which was N2H4. The final step is to subtract this amount in moles from the original amount that we calculated in the previous slide. So that's 0.815 minus 0.780, which gives us 0.0350 moles of N2O4 remaining. So let's move on to our next example. 3 grams of zinc is reacted with 50 centimeters cubed of 1 mole per decimeter cubed HCl, which is hydrochloric acid. Determine the limiting and excess reactants. So first we'll determine the amount in moles of zinc. So like in the previous example, we'll divide the mass by the molar mass, and this gives us 0.0459 moles of zinc. To determine the amount in moles of HCl, we need to use the equation N equals CV, where N equals amount in moles,
C is concentration in moles per decimeter cubed, and V is volume in decimeters cubed. Note that in the question we're given the volume of the HCl in centimeters cubed, so in this step we'll convert from centimeters cubed to decimeters cubed. So as we can see, 50 centimeters cubed is equal to 0.05 decimeters cubed. Next, we'll multiply the concentration in moles per decimeter cubed by the volume in decimeters cubed, and this gives us 0.05 moles of HCl. So the next step is to divide the amount in moles by the coefficient in the balanced equation. For zinc, the coefficient is 1, and for HCl, the coefficient is 2. So this gives us 0.0459 for the zinc and 0.0250 for the HCl. The lowest one is the limiting reactant, therefore it's the HCl, which means that zinc is the excess reactant. Next, we'll determine the amount of excess reactant that remains at the end of the reaction. To do this, we need to look at the molar ratio of zinc to HCl. From the balanced equation, we can see that 1 mole of zinc reacts with 2 moles of HCl. So in this step, we'll determine the amount in moles of zinc that react with the limiting reactant. To do this, we multiply the amount in moles of HCl by 1 over 2. This is because of the 1 to 2 molar ratio of zinc to HCl. So this gives us 0.0250 moles of zinc. So the final step is to subtract this amount from the amount in moles of zinc that we calculated in the previous slide. And this gives us 0.0209 moles of zinc remaining. So that's all from this video. In the next video, I'll be looking at how to calculate the theoretical yield. This is MSJ Chem. In this video, I'll be looking at theoretical yield and percent yield. So let's start the video by looking at some definitions. The theoretical yield is the maximum amount of product that can be formed in a chemical reaction. The theoretical yield is calculated based on the stoichiometry of the reaction and the amount of the limiting reactant. We also have the actual yield, which is the actual amount of product that is formed in a chemical reaction. Note that the actual yield is almost always less than the theoretical yield. If we know the actual yield and the theoretical yield, we can calculate the percent yield. So the percent yield is the actual yield divided by the theoretical yield multiplied by 100%. So next we look at some examples. In our first example, 100 grams of iron oxide is reacted with 100 grams of carbon. The actual yield of iron produced is 46.73 grams. Calculate the percent yield of iron. The first step is to determine which reactant is the limiting reactant. To do this, we need to convert from mass in grams to amount in moles. For iron oxide, we have 0.6262 moles. And for carbon we have 8.326 moles. The next step is to divide each amount in moles by its coefficient in the balanced equation. For iron oxide the coefficient is 2, and for carbon the coefficient is 3, and this gives us 0.3131 for iron oxide and 2.775 for carbon. The lowest value is the limiting reactant, so iron oxide is the limiting reactant and carbon is the excess reactant. Next, we'll calculate the theoretical yield of iron. To do this, we need to know the molar ratio of the limiting reactant, which is iron oxide, to the product in question, which is iron. So from the balanced equation, we can see the molar ratio is 2 to 4. So the next step is to multiply the amount in moles of our limiting reactant, which is iron oxide, by 4 over 2. This is because of the molar ratio of iron oxide to iron, and this gives us 1.252 moles of iron. The next step is to convert from amount in moles to mass in grams. To do this, we multiply the amount in moles of iron by the molar mass of iron, which is 55.85 grams per mole, and this gives us 69.92 grams of iron. So to summarize, the theoretical yield of iron is 69.92 grams. So the final step is to calculate the percent yield. The actual yield which was given in the question is 46.73 grams, and the theoretical yield which we calculated in the previous slide is 69.92 grams. And this gives us a percent yield of 66.83%. In the next example, 15 grams of calcium carbonate is reacted with 50 centimeters cubed of 2 mole per decimeter cubed HCl, which is hydrochloric acid. So the actual yield of carbon dioxide is 1.85 grams. Just like in the previous example, we need to calculate the theoretical yield of carbon dioxide. So we'll start by calculating the amount in moles of calcium carbonate and HCl. For the calcium carbonate, we divide the mass by its molar mass, which gives us 0.150 moles. For the HCl, we're using the equation N equals CV. So we multiply the concentration in moles per decimeter cubed by the volume in decimeters cubed, which gives us 0.1 moles of HCl. Next, we determine which one is the limiting reactant and which is the excess reactant. To do this, we divide the amount in moles by the coefficient in the balanced equation, and this gives us 0.150 for the calcium carbonate and 0.05 for the HCl. So the hydrochloric acid is the limiting reactant and the calcium carbonate is the excess reactant. Next, we'll calculate the theoretical yield of carbon dioxide. To do this, we need to look at the molar ratio of HCl to CO2. From the balanced equation, we can see the ratio is 2 to 1. In this step, we'll multiply the amount in moles of HCl by 1 over 2, which gives us 0.05 moles of carbon dioxide. In the next step, we'll convert from amount in moles to mass in grams. So we'll multiply the amount in moles of carbon dioxide by the molar mass, which gives us 2.20 grams of carbon dioxide. So to summarize, the theoretical yield of carbon dioxide is 2.20 grams. The final step is to calculate the percent yield. The actual yield is 1.85 grams and the theoretical yield is 2.20 grams. And this gives us a percent yield of 84.1%.
This is MSJ Chem. In this video, I'll be looking at calculating percentage purity. Percentage purity is the percentage of a pure compound in an impure sample. Here we have the equation for calculating percentage purity. So it's the mass of the pure compound in the sample divided by the total mass of the impure sample multiplied by 100. So next we look at a simple example. A 150 gram sample of copper ore contains 87.3 grams of pure copper. Calculate the percentage purity. So to calculate the percentage purity, we divide the mass of the pure copper, which is 87.3 grams, by the total mass of the impure sample, which is 150 grams, and then we multiply by 100. And this gives us 58.2%. Next, we look at some more complicated examples. 5 grams of an impure sample of hydrated ethane dioic acid was dissolved in water to make 1 decimeter cubed of solution. 25 centimeter cubed samples of this solution were titrated against a 0.1 mole per decimeter solution of sodium hydroxide using a suitable indicator. The average volume of the titer, which is sodium hydroxide, was 14 centimeters cubed. Using this information, we'll calculate the percentage purity of the hydrated ethane dioic acid. So we'll start by looking at the balanced equation for the reaction. 1 mole of ethane dioic acid reacts with 2 moles of sodium hydroxide to form 1 mole of salt and 2 moles of water. Note that the ethane dioic acid reacts with the sodium hydroxide in a 1:2 ratio. The first step is to calculate the amount in moles of sodium hydroxide in the average titer. So we use the equation N equals CV. The concentration of sodium hydroxide is 0.1 mole per decimeter. The average titer was 14.0 centimeters cubed, which we convert to decimeters cubed by dividing by 1000. This gives us 1.40 times 10 to the negative 3 moles. The second step is to calculate the amount in moles of ethane dioic acid
that reacts with the sodium hydroxide. The molar ratio of ethane dioic acid to sodium hydroxide is a 1:2 ratio, so we divide the amount in moles of sodium hydroxide by 2, which gives us 7.00 times 10 to the negative 4 moles. Next, we calculate the amount in moles of ethane dioic acid in 1 decimeter cubed of solution. So we multiply the amount in moles in 25 centimeters cubed of solution by 1000 over 25, which gives us 2.80 times 10 to the negative 2 moles. Next, we convert amount in moles to mass in grams. So we multiply the amount in moles of ethane dioic acid in 1 decimeter cubed of solution by the molar mass of ethane dioic acid, which gives us 3.53 grams. And finally, we'll calculate the percentage purity. So we divide the mass of the pure ethane dioic acid by the total mass of the impure sample. We then multiply by 100 to give us 70.6%. Next, we look at one more example. 10 grams of chalk, which is impure calcium carbonate, was reacted with excess hydrochloric acid. So here we have the equation for the reaction. 1 mole of calcium carbonate reacts with 2 moles of hydrochloric acid to form 1 mole of salt, 1 mole of carbon dioxide, and 1 mole of water. We are also told that 2.13 decimeters cubed of carbon dioxide was produced at STP in the reaction. The first step is to calculate the amount in moles of carbon dioxide produced in the reaction. So we divide the volume of carbon dioxide produced in the reaction by the molar volume of a gas at STP, which is 22.7 decimeters cubed. This gives us 9.38 times 10 to the negative 2 moles. If we look at the molar ratio of carbon dioxide to calcium carbonate, we can see it's a 1:1 ratio. Because calcium carbonate is the limiting reactant, 9.38 times 10 to the negative 2 moles of calcium carbonate must have reacted to produce the same amount in moles of carbon dioxide. So next, we can calculate the mass of calcium carbonate that reacted with the excess hydrochloric acid. So we multiply the amount in moles by the molar mass of calcium carbonate, which is 100.09 grams per mole. And this gives us 9.38 grams. And finally, we calculate the percentage purity. So it's the mass of the pure sample of calcium carbonate, which was 9.38 grams, by the total mass of the impure sample, which was 10.00 grams. We then multiply this by 100 to give us 93.8%. This is MSJ Chem. In this video, I'll be looking at the molar volume of a gas. The molar volume of a gas is the volume occupied by 1 mole of an ideal gas. The molar volume must be stated at specific conditions. In this video, I'll be using the conditions of STP. These are a temperature of 273 Kelvin and a pressure of 100,000 pascals. Here we can see these values plugged into the ideal gas equation, which has been rearranged to calculate for volume. As we can see, this gives us a volume of 0.0227 meters cubed. The molar volume can be determined by dividing the volume by the amount in moles. In this equation, we have a volume of 0.0227 meters cubed, which is the volume occupied by 1 mole of an ideal gas. So this gives us the molar volume of an ideal gas under conditions of STP, which is 0.0227 meters cubed per mole, or 22.7 decimeters cubed per mole. In the previous slide, we defined the molar volume of a gas as the volume occupied by 1 mole of an ideal gas under conditions of STP. Under these conditions, real gases such as oxygen, hydrogen, and chlorine behave almost the same as ideal gases. For example, 1 mole of oxygen gas under conditions of STP will occupy a volume of 22.7 decimeters cubed. The same is true for 1 mole of hydrogen gas and 1 mole of chlorine gas. So we can now say that under conditions of STP, 1 mole of any gas, be it an ideal gas or a real gas, occupies a volume of 0.0227 meters cubed, which is more commonly given as 22.7 decimeters cubed. Next, we'll look at equations that can be used to calculate either the volume or the amount in moles of a gas. The first equation we look at is used to calculate volume. To calculate the volume of a gas, multiply the amount in moles by the molar volume. An easy way to remember this equation is V equals N multiplied by 22.7. Note that this equation will give you the volume in decimeters cubed. The next equation is used to calculate the amount in moles. To calculate the amount in moles, divide the volume by the molar volume. Once again, an easy way to remember this equation is N equals V divided by 22.7. In the first example, we'll calculate the volume in decimeters cubed occupied by 0.250 moles of nitrogen gas at STP. The equation that we'll use is volume equals amount in moles multiplied by the molar volume of a gas. So the volume is equal to 0.250 multiplied by 22.7, and this gives a volume of 5.68 decimeters cubed. Note that the unit of volume in the answer is the same as that in the question, which is decimeters cubed. The next example is calculate the volume in centimeters cubed occupied by 0.00619 moles of carbon dioxide at STP. So first, we'll calculate the volume in decimeters cubed and then convert to centimeters cubed. To do this, we multiply the amount in moles by the molar volume, and this gives us 0.141 decimeters cubed. Because the question is asking for the volume in centimeters cubed, the final step is to convert from decimeters cubed to centimeters cubed. 1 decimeter cubed is equal to 1000 centimeters cubed, so we multiply this volume in decimeters cubed by 1000, and this gives a volume of 141 centimeters cubed of carbon dioxide. In the next example, we'll calculate the amount in moles of nitrogen in a 0.742 decimeter cubed sample. So we'll use this equation, which is N equals V divided by 22.7. The volume of nitrogen is 0.742 decimeters cubed, which we then divide by the molar volume of a gas at STP, and this gives us an amount of nitrogen of 0.0327 moles. In the next example, we'll calculate the amount in moles of CH4, which is methane, in a 2.36 centimeter cubed sample at STP. The first step in this calculation is to convert the volume from centimeters cubed to decimeters cubed. So 2.36 centimeters cubed is equal to 2.36 times 10 to the negative 3 decimeters cubed. We can then use the same equation as in the previous slide, which is N equals V divided by 22.7. So as we just calculated, the volume of CH4 is 2.36 times 10 to the negative 3 decimeters cubed, which we then divide by the molar volume of a gas at STP, which gives us an amount of methane of 1.04 times 10 to the negative 4 moles. In the last example, we'll determine the volume of hydrogen in centimeters cubed produced at STP when 2 grams of magnesium is reacted with excess hydrochloric acid. So here we have the balanced equation for the reaction. Magnesium reacts with hydrochloric acid to produce magnesium chloride and hydrogen gas. The first step is to determine the amount in moles of magnesium. To do this, we divide the mass of magnesium by the molar mass, which gives us 0.0823 moles. We then use the balanced equation to determine the ratio of magnesium to hydrogen. So from the balanced equation, we can see it's a 1-to-1 ratio. So this means that 0.0823 moles of magnesium will produce the same amount, which is 0.0823 moles of hydrogen. So in the previous slide, we determined the amount in moles of hydrogen that will be produced in the reaction. Next, we'll convert the amount in moles to volume. We'll use the equation volume equals amount in moles multiplied by 22.7. So that's 0.0823 multiplied by 22.7, which gives a volume of 1.87 decimeters cubed.
In the final step, we'll convert from decimeters cubed to centimeters cubed. So 1.87 decimeters cubed is equal to 1.87 times 10 to the 3 centimeters cubed. So this is the volume of hydrogen gas produced in the reaction. This is MSJ Chem. In this video, I'll be looking at the gas laws. In this video, I'll be looking at the following gas laws. The first gas law is the relationship between pressure and volume at constant temperature, which is also known as Boyle's law. Next is the relationship between volume and temperature at constant pressure, which is also known as Charles's law. We'll also look at the relationship between pressure and temperature at constant volume, which is also known as Gay-Lussac's law. After that, we'll look at the relationship between volume and amount in moles at constant temperature and pressure, which is also known as Avogadro's law. And finally, we'll look at the combined gas law. We'll start by looking at the relationship between pressure and volume at constant temperature, which is also known as Boyle's law. This states that the volume occupied by a gas is inversely proportional to its pressure. In equation form, Boyle's law can be represented in three different ways. The first is the pressure multiplied by the volume is equal to a constant K. The second is that pressure is directly proportional to 1 over volume. And the third way is P1 multiplied by V1 equals P2 multiplied by V2. Graphically, Boyle's law can be represented in two different ways. On the left, we have a graph of pressure against volume. From the graph, we can see that as the pressure decreases, the volume increases. On the right, we have a graph of pressure against 1 over volume. The straight line produced shows that pressure is directly proportional to 1 over volume. Next, we have the relationship between volume and temperature at constant pressure, which is also known as Charles's law. This states that the volume occupied by a gas is directly proportional to its absolute temperature in Kelvin. In equation form, this can be represented as V is directly proportional to T. It can also be represented as V over T equals a constant K. On the right, we have a graph of volume against absolute temperature in Kelvin. From the graph, we can see that volume is directly proportional to temperature in Kelvin. Charles's law can also be represented as V1 over T1 is equal to V2 over T2. The next gas law that we look at is the relationship between pressure and temperature at constant volume, which is also known as Gay-Lussac's law. This states that the pressure exerted by a gas is directly proportional to its absolute temperature in Kelvin. This can be represented as P is directly proportional to T, or P over T is equal to a constant K. On the right, we have a graph of pressure against absolute temperature in Kelvin. From the graph, we can see that pressure is directly proportional to temperature in Kelvin. Gay-Lussac's law can also be represented as P1 over T1 is equal to P2 over T2. The next gas law that we look at is the relationship between volume and amount in moles at constant pressure and temperature, which is also known as Avogadro's law. This states that the volume occupied by a gas is directly proportional to the amount in moles of gas. So in equation form, this can be written as V is directly proportional to N, or V over N is equal to a constant K. On the right, we have a graph of volume against amount in moles of a gas. From the graph, we can see that volume is directly proportional to amount in moles. Another way of representing Avogadro's law is V1 over N1 is equal to V2 over N2. The final gas law that we look at is the combined gas law, which combines Boyle's law, Charles's law, and Gay-Lussac's law. So the combined gas law is P1 multiplied by V1 divided by T1 is equal to P2 multiplied by V2 divided by T2. The combined gas law can also be represented as P1 multiplied by V1 divided by T1 is equal to a constant K. So that's all from this video. In the next video, I'll be going through examples of all the gas laws. This is MSJ Chem. In this video, I'll be looking at examples involving the gas laws. In our first example, we have a sample of gas with a volume of 15 cubic centimeters
at a pressure of 575 kilopascals. Assuming that temperature remains constant, what volume will the gas occupy at a pressure of 968 kilopascals? To solve this problem, we'll use the equation P1 times V1 is equal to P2 times V2, which is Boyle's law. In the question, we are given P1, V1, and P2, so we need to solve for V2. So here we have the equation rearranged to solve for V2. Next, we substitute the values into the equation. P1 is 575 kilopascals, and V1 is 15.0 cubic centimeters. P2 is 968 kilopascals. And this gives us a value for V2 of 8.91 cubic centimeters. In our next example, we have a sample of gas with a volume of 32.0 cubic decimeters at a temperature of 256 Kelvin. Assuming that pressure remains constant, what volume will the gas occupy at a temperature of 391 Kelvin? To solve this, we'll use this equation, which is Charles's law. In the question, we're given V1, T1, and T2. So we need to rearrange this equation to solve for V2. And V2 is equal to V1 times T2 divided by T1. So next, we substitute the values into the equation. V1 is 32.0 cubic decimeters, and T2 is 391 Kelvin. T1 is 256 Kelvin, and this gives us a value for V2 of 48.9 cubic decimeters. In our next example, we have a sample of gas with a pressure of 73.9 kilopascals at a temperature of 347 Kelvin. Assuming that volume remains constant, what will be the pressure of the gas at a temperature of 602 Kelvin? So here we have the equation for Gay-Lussac's law. In the question, we're given P1, T1, and T2. So we need to solve for P2. And here we have the equation rearranged to solve for P2. Next, we substitute the values into the equation. P1 is 73.9 kilopascals. T2 is 602 Kelvin. And T1 is 347 Kelvin. And this gives us a value for P2 of 128 kilopascals. In the next example, a sample contains 5.13 moles of gas with a volume of 1.28 cubic meters. Assuming that temperature and pressure remain constant, what volume will the gas occupy if 3.49 moles of gas are added? So here we have the equation for Avogadro's law. In the question, we're given V1 and N1. To find N2, we need to add the two amounting moles of gas, which is 5.13 plus 3.49. To find V2, we need to rearrange the equation. So V2 equals V1 times N2 divided by N1. V1 is 1.28 cubic meters, N2 is 8.62 moles, and N1 is 5.13 moles. And this gives us a value for V2 of 2.15 cubic meters. In our last example, a sample of gas has a volume of 1.54 cubic meters at a temperature of 447 Kelvin and a pressure of 12.0 kilopascals. If the temperature and pressure are changed to 561 Kelvin and 15.7 kilopascals respectively, what volume will the gas occupy? To solve this, we'll use the combined gas law. In the question, we're given P1, V1, T1, P2, and T2. So we need to rearrange the equation to solve for V2. And V2 equals V1 times P1 times T2 divided by T1 times P2. V1 is 1.54 cubic meters. P1 is 12.0 kilopascals. T2 is 561 Kelvin. T1 is 447 Kelvin. And P2 is 15.7 kilopascals. So this gives us a value for V2 of 1.48 cubic meters.
This is MSJ Chem. In this video, I'll be looking at Avogadro's law. Avogadro's law was covered in a previous video, and we saw that the volume occupied by a gas is directly proportional to the amount in moles of gas at constant pressure and temperature. This can be shown as V is directly proportional to N,
V over N equals a constant K, or V1 over N1 is equal to V2 over N2. Avogadro's law can also be expressed as the following. At the same temperature and pressure, equal volumes of any gas contain the same number of particles. So this tells us that for any gas, equal volumes at the same temperature and pressure will contain the same number of particles. So next we look at some examples. In this table we have the gases oxygen, hydrogen, nitrogen, carbon dioxide and methane. As we can see, 1 mole of each gas has a volume of 22.7 cubic decimeters under conditions of STP, which is 22.7 cubic decimeters. If we look at the right column, we can see that 1 mole of each gas contains the same number of particles, which is 6.02 times 10 to the power of 23. So from this table, we can see that equal volumes of any gas at the same temperature and pressure have the same number of particles, which is Avogadro's law. So next, we look at some example problems. In the first example, we'll look at the reaction between carbon monoxide and oxygen to produce carbon dioxide. According to the balanced equation, 2 moles of carbon monoxide react with 1 mole of oxygen to produce 2 moles of carbon dioxide. If the reaction is carried out at a fixed temperature and pressure, we can treat the mole ratios as volume ratios. So we can say that 2 volumes of carbon monoxide will react with 1 volume of oxygen to produce 2 volumes of carbon dioxide. So 2 cubic decimeters of carbon monoxide will react with 1 cubic decimeter of oxygen to produce 2 cubic decimeters of carbon dioxide. And 10 cubic decimeters of carbon monoxide will react with 5 cubic decimeters of oxygen to produce 10 cubic decimeters of carbon dioxide. So to summarize, if a reaction is carried out at a fixed temperature and pressure, we can treat the mole ratios as volume ratios. So next we look at some examples. In our first example, 40 cubic decimeters of carbon monoxide is reacted with 40 cubic decimeters of oxygen at STP. Determine the volume of carbon dioxide produced. So the first step is to determine the limiting reactant. To do this, we can divide the volume of each reactant by its coefficient in the balanced equation. So for carbon monoxide, that's 40 divided by 2, which gives us 20. And for oxygen, it's 40 divided by 1, which gives us 40. The lowest value, which is carbon monoxide, is the limiting reactant, and oxygen is the excess reactant. If we look at the coefficients in the balanced equation, we can see that 2 moles of carbon monoxide will produce 2 moles of carbon dioxide. So 40 cubic decimeters of carbon monoxide will produce the same volume, which is 40 cubic decimeters of carbon dioxide. In our next example, we have 20 cubic decimeters of nitrogen reacting with 50 cubic decimeters of hydrogen at STP. Determine the volume of ammonia produced and the volume of the excess reactant remaining. So in this reaction, which is known as the Haber process, nitrogen and hydrogen react together to form ammonia. Like in the previous example, the first step is to determine the limiting reactant. So for nitrogen, we divide the volume by the coefficient in the balanced equation, which gives us 20. If we do the same for hydrogen, we get 16.7, which tells us that hydrogen is the limiting reactant. If we look at the molar ratio of hydrogen to ammonia, we can see it's a 3:2 ratio. This means that 50 cubic decimeters of hydrogen will produce 2/3 as much ammonia, which is 33.3 cubic decimeters. Next, we'll calculate the volume of the excess reactant remaining. To do this, we look at the molar ratio of nitrogen to hydrogen, which we can see is a 1:3 ratio. This tells us that 50 cubic decimeters of hydrogen will react with 1/3 as much nitrogen, which is 16.7 cubic decimeters. So to calculate the volume of nitrogen remaining, we subtract 16.7 from 20, which gives us 3.3 cubic decimeters.
This is MSJ Chem. In this video, I'll be looking at the ideal gas equation. In previous videos, we've looked at 3 gas laws. They are Boyle's law, Charles's law, and Avogadro's law. These 3 laws can be combined to form a new expression. This new expression shows that the volume of a gas is directly proportional to the amount in moles and the temperature, and inversely proportional to the pressure.
The proportionality constant in this equation is given the letter R, which is the universal gas constant. This equation can then be rearranged to give the most common form of the ideal gas equation, which is PV equals nRT. So here we have the ideal gas equation, which is PV equals nRT. P is pressure in pascals. V is volume in meters cubed. N is amount in moles. R is the gas constant, which has a fixed value of 8.31 joules per Kelvin mole. And T is the temperature in Kelvin. So next we look at how the ideal gas equation can be rearranged to calculate for N, V, P or T. So N, which is amount in moles, is equal to PV over RT, and V, which is volume in meters cubed, equals nRT over P. P, which is pressure in pascals, equals nRT over V, and T, which is temperature in Kelvin, equals PV over nR. So next, we'll look at some examples. In the first example, we'll calculate the volume in cubic decimeters occupied by 0.5 moles of gas at 150,000 pascals and 25 degrees C. So we'll use this equation to calculate the volume. The amount in moles is 0.5, the universal gas constant is 8.31 joules per Kelvin mole, and the temperature in Kelvin is 298. We then multiply these together and divide by the pressure, which is 150,000 pascals. This gives us a volume of 8.25 times 10 to the negative 3 cubic meters. To convert to cubic decimeters, we multiply the volume in cubic meters by 1000, which gives us 8.25 cubic decimeters. In the next example, we'll calculate the pressure in kilopascals of 0.2 moles of gas that occupies a volume of 10 cubic decimeters at 20 degrees C. So we'll use this equation to calculate the pressure. So we have the amount in moles, which is 0.2, the universal gas constant, and the temperature in Kelvin, which is 293. We then multiply these together and divide by the volume in cubic meters. And this gives a pressure of 4.87 times 10 to the 4 pascals. To convert from pascals to kilopascals, we divide by 1000, which gives us 48.7 kilopascals. In the next example, we'll calculate the amount in moles of gas that occupies a volume of 20 cubic decimeters at 50 degrees C and 0.850 kilopascals. So to calculate amount in moles, we'll use this equation. The pressure in pascals is 85,000. The volume in cubic meters is 0.02. The universal gas constant is 8.31 joules per Kelvin mole, and the temperature in Kelvin is 323. And this gives us an amount of 0.633 moles. This is MSJ Chem. In this video, I'll be looking at deviation from ideal gas behaviour. An ideal gas is a hypothetical gas that obeys the gas laws and the kinetic molecular theory. The kinetic molecular theory states the following. Particles of an ideal gas are in constant, random, straight-line motion. Collisions between particles of an ideal gas are elastic, which means that total kinetic energy is conserved. The volume occupied by the particles of an ideal gas is negligible relative to the volume of the container. There are no intermolecular forces acting between particles of an ideal gas. And finally, the average kinetic energy of the particles of an ideal gas is directly proportional to the absolute temperature in Kelvin. A real gas is a gas that deviates from ideal gas behavior. For example, real gases have a finite measurable volume. They also have intermolecular forces that act between the particles. Real gases exhibit nearly ideal behavior at relatively high temperatures and low pressures. They deviate the most from ideal behavior at low temperatures and high pressures. In this table, we have the molar volumes for a range of real gases as well as an ideal gas. For an ideal gas, we have a value of 22.414 cubic decimeters per mole. If we look at the molar volumes for the real gases under these conditions, we can see that they are similar. This tells us that real gases behave almost ideally under these conditions. However, as mentioned in the previous slide, real gases deviate from ideal behavior at low temperatures and high pressures, which we'll look at next. For 1 mole of an ideal gas, the product of PV over RT is always equal to 1. Here we have the ideal gas equation that's been rearranged to solve for N, which is amount in moles. If we substitute in the values for the pressure and temperature at STP, we get a value of 1 mole. As we'll see in the next slide, for real gases, the product of PV over RT is not equal to 1. In this graph, on the y-axis, we have the product of PV over RT. On the x-axis, we have pressure. From the graph, we can see that for an ideal gas, the product of PV over RT is equal to 1 at all pressures. The 3 curves on the graph show the deviation of nitrogen from ideal behavior at 3 different temperatures. The greatest deviation from ideal behavior occurs at 200 Kelvin. This tells us that real gases deviate the most from ideal gas behavior under 2 conditions: high pressures and low temperatures. On the graph, we can see that at moderately high pressures, the product of PV over RT is less than 1, and at very high pressures, the product of PV over RT is greater than 1. So as we saw in the previous slide, at moderately high pressures, the values of PV over RT are less than 1, which is mainly because of the effects of intermolecular forces. In this diagram, we can see that at lower external pressures, the particles are too far apart for intermolecular forces to act. As the external pressure increases, the particles are forced closer together. On the right, we can see the effect of this increased pressure on the intermolecular forces of a gas. Intermolecular attractions between the gas particles reduce the force of the collisions with the container wall, which results in a lower pressure. Because the pressure of the gas becomes less than expected, the product of PV over RT is less than 1. So to summarize, at moderately high pressures, the deviation from ideal gas behavior is mainly because of the effects of intermolecular forces. Next, we'll look at the cause of the deviation from ideal behavior at very high pressures. As we saw previously, at very high pressures, the values of PV over RT are greater than 1. This is mainly because of the effects of molecular volume. From the diagram, we can see that at lower external pressures, the volume occupied by the gas particles is negligible compared to the volume of the container. At very high external pressures, the volume occupied by the gas particles becomes significant. The V in PV over RT is the volume of the container. However, the volume available for the gas particles is less than the container volume. Therefore, the product of PV over RT is greater than 1. So to summarize, at very high pressures, the deviation from ideal behavior is mainly because of the effects of molecular volume. So far in this video, we've considered the effects of intermolecular forces and pressure on the deviation of a real gas from ideal gas behavior. Next, we'll consider the temperature. At lower temperatures, the particles in a real gas have lower average kinetic energy, and the particles of a real gas at higher temperatures have higher average kinetic energy. Because the particles of a gas at lower temperatures are moving more slowly, they are less able to overcome the effects of the intermolecular forces. At higher temperatures, for example 1000 Kelvin, the particles of the gas have sufficient kinetic energy to overcome the effects of the intermolecular forces. So as we can see, as temperature increases, real gases behave more ideally, and at lower temperatures they show the greatest deviation from ideal gas behavior. On this graph, we can see the deviation from ideal behavior for 4 different gases. They are hydrogen, nitrogen, methane, and carbon dioxide. From the graph, we can see that each gas differs in its deviation from ideal behavior. At moderately high pressures, we can see that carbon dioxide and methane show significant deviation from ideal behavior, whereas hydrogen and nitrogen show less deviation. Previously, we saw that the deviation at moderately high pressures was because of the effect of intermolecular forces. Both carbon dioxide and methane have stronger intermolecular forces between their molecules than nitrogen and hydrogen. Therefore, they show the greatest deviation at moderately high pressures. The gas that shows the least deviation from ideal behaviour is hydrogen. This is because of its low molar mass, which results in weak London dispersion forces between its molecules. So to summarise, gases with weak intermolecular forces will show less deviation from ideal gas behaviour, and gases with stronger intermolecular forces will show more deviation from ideal gas behaviour. We'll end the video with a comparison of ideal gases and real gases. As we've seen, ideal gases behave ideally at all temperatures and pressures. Real gases, on the other hand, deviate the most from ideal behaviour at low temperatures and high pressures. The volume occupied by an ideal gas is assumed to be negligible. However, real gases have a finite measurable volume. Ideal gases have no intermolecular forces acting between the particles. Real gases do have intermolecular forces acting between their particles. And finally, ideal gases obey the ideal gas law, which is PV equals nRT. Real gases obey the van der Waals equation, which we'll look at in more detail in the next video. This is MSJ Chem. In this video, I'll be looking at calculating the molar mass of a gas using the ideal gas equation. We'll start by looking at an example. 1.10 grams of an unknown gas occupies a volume of 567 centimeters cubed at STP. Calculate the molar mass of the gas. To solve this, we'll use the equation molar mass equals mRT divided by PV. M is molar mass in grams per mole, small m is mass in grams, R is a universal gas constant, P is the pressure in pascals, and V is the volume in meters cubed. So here we have the same equation with the values substituted in. The mass of the gas is 1.10 grams, the universal gas constant is 8.31 joules per Kelvin mole, the temperature in Kelvin at STP is 273. The pressure of a gas at STP is 1.00 times 10 to the 5 pascals. And to convert from centimeters cubed to meters cubed, we divide the value in centimeters cubed by 1 million. This gives us a molar mass of 44.0 grams per mole. This is MSJ Chem. In this video, I'll be looking at determining the molar mass of a gas experimentally. The molar mass of a gas, such as butane, can be determined experimentally. To collect the gas, a measuring cylinder is inverted and filled with water. The measuring cylinder is filled with a known volume of gas from a cigarette lighter. The mass of the cigarette lighter is recorded before and after the measuring cylinder is filled. To calculate the molar mass of the gas, we need to know the change in mass of the lighter, the volume of gas collected, and the pressure and the temperature. We then use this equation to calculate the molar mass of the gas, which is mass times the universal gas constant times the temperature in Kelvin divided by the pressure multiplied by the volume. So we start with a change in mass of the lighter, which is 0.230 grams. We then have the volume of gas collected, which is 100.0 centimeters cubed. Note we need to convert this to meters cubed to use the ideal gas equation. The temperature of the gas was 22.0 degrees C, which we need to convert to Kelvin. Next, we have the atmospheric pressure and the vapor pressure of water at 22.0 degrees C. To find the pressure of the butane in the measuring cylinder, we subtract the vapor pressure of water from the atmospheric pressure. And finally, we have the universal gas constant, which is 8.314 joules per Kelvin mole. We then input these values into the equation, taking care to use the correct units. And this gives us a molar mass of butane of 57.5 grams per mole. Next, if we calculate the molar mass of butane using the molar masses of carbon and hydrogen, we get 58.14 grams per mole. Next, we can calculate the percentage error. So that's the experimental minus the theoretical divided by the theoretical multiplied by 100, which gives us a percentage error of -1%. The negative percentage error tells us that our experimental value was less than the theoretical value. Finally, we look at why our experimental value is different to the theoretical value. So we'll start by looking at errors that make the molar mass lower than the actual. The first is where the lighter is not dried completely before recording the mass.
Next, we have the pressure of the gas not equalized with the pressure of the room. And we have the lighter may contain a mixture of propane and butane. And for errors that make the molar mass higher than the actual, we have some bubbles of gas escaped from the cylinder. So that's all from this video. Be sure to check out my other videos at my website www.msjchem.com. This is MSJ Chem. In this video, I'll be looking at how to calculate the concentration of solutions. The concentration of a solution can be measured in grams per cubic decimeter, moles per cubic decimeter, or ppm. The first equation shows how to calculate concentration in grams per cubic decimeter, which is the mass of the solute in grams divided by the volume of the solution in cubic decimeters. To calculate the concentration of a solution in moles per cubic decimeter, divide the amount of solute in moles by the volume of the solution in cubic decimeters. And to calculate the concentration of a solution in ppm, which is parts per million, divide the mass of solute in grams by the mass of solution in grams and multiply by 10 to the power of 6. So next we look at some examples. In our first example, we have a solution with a volume of 500 cubic centimeters that contains 12.50 grams of sodium chloride. Calculate its concentration in grams per cubic decimeter. So to do this, we'll divide the mass of the solute in grams by the volume of the solution in cubic decimeters. So next, we substitute the values into the equation. The mass of sodium chloride is 12.50 grams, and the volume of the solution is 500 cubic centimeters. Because the concentration is measured in grams per cubic decimeter, we need to convert cubic centimeters to cubic decimeters. To do this, we divide the volume in cubic centimeters by 1000. So 500 cubic centimeters is 0.5 cubic decimeters. So when we divide the mass of sodium chloride by the total volume of the solution, we get a concentration of 25.00 grams per cubic decimeter. So next we'll calculate the concentration of the same solution, but this time in moles per cubic decimeter. To do this, we divide the amount of solute in moles by the volume of the solution in cubic decimeters. So the first step is to convert from mass in grams to amount in moles. The mass of sodium chloride is 12.50 grams, and the molar mass of sodium chloride is 58.44 grams per mole. If we divide the mass by the molar mass, we get the amount in moles, which is 0.2139. The final step is to divide the amount in moles by the volume in cubic decimeters, and this gives us a concentration of 0.4278 moles per cubic decimeter. In the last example, we'll calculate concentration in ppm, which is parts per million. A 300 gram water sample contains 1.514 times 10 to the negative 3 grams of dissolved oxygen. Calculate the concentration in ppm. So we'll use this equation, which is the mass of the solute divided by the mass of the solution multiplied by 10 to the power of 6. So the mass of oxygen is 1.514 times 10 to the negative 3 grams. And the solution has a mass of 300 grams. And this gives us a concentration of 5.047 ppm. 1 ppm is equal to 1 milligram per cubic decimeter. So we can also give the answer as 5.047 milligrams per cubic decimeter. This is MSJ Chem. In this video, I'll be looking at the technique of back titration. A back titration or indirect titration has two stages. In the first stage, one reactant of unknown concentration is reacted with an excess reactant of known concentration. In the second stage, the amount of excess reactant is determined by a direct titration. Back titrations are often used when one reactant is insoluble in water, for example salts such as calcium carbonate. A common experiment using a back titration is to determine the percentage calcium carbonate in an eggshell. So next we look at an example of how to do this. A student carried out an experiment to determine the percentage calcium carbonate in an eggshell. A 0.4 gram sample of eggshell was crushed up and reacted with 25 centimeters cubed of 0.5 mole per decimeter cubed hydrochloric acid.
Here we can see the reaction that takes place between calcium carbonate and hydrochloric acid. The calcium carbonate in the eggshell reacts with hydrochloric acid to produce the salt calcium chloride, water, and carbon dioxide gas. Next, the excess acid was titrated with 0.5 mole per decimeter cubed sodium hydroxide. The average titer was 12.10 centimeters cubed. And here we have the reaction between sodium hydroxide and hydrochloric acid. The products of the reaction are sodium chloride and water. The first step is to determine the amount in moles of hydrochloric acid in 25 centimeters cubed of 0.5 mole per decimeter cubed HCl. To do this, we use the equation N equals CV, where N is amount in moles, C is concentration, and V is volume in decimeters cubed. So we have 0.5 times 25 divided by 1000. We divide by 1000 to convert from centimeters cubed to decimeters cubed, which gives us 0.0125 moles. Next, we determine the amount in moles of excess hydrochloric acid. To do this, we calculate the amount in moles of sodium hydroxide that reacted with the excess hydrochloric acid. So that's 0.5 times 12.10 divided by 1000. And this gives us 6.05 times 10 to the negative 3 moles. If we look at the balanced chemical equation between sodium hydroxide and hydrochloric acid, we can see the molar ratio is 1:1. Because of this, the amount in moles of sodium hydroxide is equal to the amount in moles of excess hydrochloric acid. So the amount in moles of excess hydrochloric acid is 6.05 times 10 to the negative 3 moles. Next, we'll determine the amount in moles of hydrochloric acid that reacted with the calcium carbonate in the eggshell. To do this, we subtract the amount in moles of hydrochloric acid that was in excess from the initial amount of hydrochloric acid. So that's 0.0125 minus 6.05 times 10 to the negative 3, which gives us 6.45 times 10 to the negative 3 moles. Next, we'll determine the amount in moles of calcium carbonate in the eggshell. Here we can see the balanced chemical equation between calcium carbonate and hydrochloric acid. As we can see, the molar ratio of calcium carbonate to hydrochloric acid is 1:2. So next, we divide the amount of hydrochloric acid that reacted with the calcium carbonate by 2. This is because of the 1:2 molar ratio of calcium carbonate to hydrochloric acid. So the amount of hydrochloric acid that reacted with the calcium carbonate is 6.45 times 10 to the negative 3, which we then divide by 2, which gives us 3.23 times 10 to the negative 3 moles. The final step is to convert from amount in moles to mass in grams. So we use the equation mass equals amount in moles multiplied by molar mass. When we multiply these two together, we get a mass of calcium carbonate in the eggshell of 0.323 grams. And finally, we can determine the percentage of calcium carbonate in the eggshell. To do this, we divide the mass of calcium carbonate in the eggshell by the total mass of the eggshell and multiply by 100. So that's 0.323 grams divided by 0.4 grams multiplied by 100, which gives us 80.8%. This tells us that the eggshell is approximately 81% calcium carbonate by mass.